Hello, folks. Welcome to Rational Science, the only site on the internet that does physics rationally. I'm going to be talking about flavors today a little bit. That's going to be the main course. But before I get there, I want to talk a little bit about a subject which I haven't talked for a while, which is extinction. And there's a subject matter which is related to extinction. Discipline known as demography. What is demography? We're going to look at that today. And how is it related to extinction? I mean, you would think that if demography looks at population and population drops to zero, that's a subject matter that would concern demography, right? So I think demography is related in that sense to extinction. At least you would think that it's the demographers who to some degree would have a say in, what causes the extinction of man, an explanation, right? Not only paleontologists and maybe biologists, but demographers and maybe economists as well, right? Okay, so let's look at this. What is demography? Well, let's start here with a definition. This is the one we look up, and it says, the statistical study of human populations. We already have a problem there, and I talked about this the other day, the fact that you can't use the terms the study of. Anytime you define something as the study of, we're talking about irrationality. That's an irrational definition. You can study all week and get a 0 on the test. And the fact that a little boy opens a book and starts studying population, does that make him a demographer? So yeah, the study of for any discipline is a bad way to start the definition. They are all irrational definitions. In science, we do not study. Okay? We do something else in science. We'll get to that in a minute. But it says their size, composition, and how they change through interplay of fertility, birth, mortality, and migration. Well, how is not really the word. The word is why. We're not interested in a description, especially a mathematical description. We're interested in an explanation, a qualitative explanation. That's what science is about. And here from another site, you get this definition. Demography uses scientific methods. Okay, let's see what those are, including data collection and analysis. No, those two are not part of science. Okay, we don't collect data. We don't do analysis in science. You can do that on your own time. When you come to the conference, we want you to explain. And that's what comes next, the formulation of theories. Yeah, that's what we do in science. That's the only part that belongs to science and to the scientific method, okay, to understand population dynamics, okay? But then again, you see, what is a demographer? They say the study of statistics. Statistics is not part of science, okay? Statistics is a language, like, any mathematics is a language, and statistics is a branch of mathematics. None of that belongs to science. Science only explains, it doesn't describe, and that's all that math can do, including statistics, okay? And I just want to point out before leaving this picture here, that demographers usually put the S-curve, the red one there on the lower left, and that's what they call the population curve, and it always ends there. But really, they always miss the green part, okay, which is the extinction part, which comes right after the S-curve, okay? So the S-curve is always a partial population curve. The full population curve, it includes extinction. All species of plants, all species of animals become extinct at some point. Okay, that's important to note because extinction is inevitable. Okay, that's what we argue here. The extinction of any species, whether plant or animal, is inevitable. All species will become extinct one way or another. Mother Nature programs, or when she gives birth to a species, already programs the death of that species. They will die at some point. Okay, so what is our definition of science and demography? A little different than the one you just saw. Science rational explanations, that's what science is. And that excludes math. Math does not explain. That's why math is not a part of science. Math can only describe, and descriptions are not science. Physics, rational explanations of causes and mechanisms, and philosophy, the other branch of science, is rational explanations of purposes and reasons. Philosophy deals with behavior and not what anything that Plato or Aristotle or anyone after that came up with. Okay. Now, demography falls into one of these two categories because certain aspects of it are rational explanations of causes and mechanisms, and others are purposes and reasons of what related to population. Okay. So some aspects are physics, some aspects are philosophy. What's here are two examples. Physics. What causes the extinction of a population? That's a question, that relates to physics. Or what mechanisms led to 75% whites versus 15% blacks in the U.S.? Now you're talking about a mechanism, what caused it. Okay, that's a question of physics. Whereas philosophy, talking about primarily free will, whereas physics is merely deterministic, right? Objects, things, or mechanisms, unavoidable mechanisms. Here we're talking about philosophy. Here's what purposes or reasons do people have babies, or why are people moving from the rural to urban areas? Those are questions of philosophy. Okay, so you can say that demography is divided into these different subjects. And, whether you do the physical part or the philosophy part, depends on whether you're dealing with causes and mechanisms or purposes and reasons. Okay, here I looked up some of the famous demographers, past and present. Okay, and this is what the AI told me. Spitted out some names. And the problem here is that most of these people do not do explanations. What they do is descriptions, again, because they think that demography is about statistics and collecting data and just spitting out facts as they see it. Okay, and most of the work of these people has to do with math, with statistics. And at the bottom you see the doomsday equation by this fellow Forster, and doomsday argument, which was enunciated by several people, among them Carter, Leslie, and Gott, right? It's interesting, this fellow Forster there, he's got a, let me put him up here, he's got a doomsday equation, and it's coming up soon on 2026, okay? And he says, doomsday equation for the Earth's population, the whole planet, right? And he says, predicts it will happen on the 13th of November, 2026. This will be the population or demographic high point, okay? It's the, the point where he says that after that we will become infinite. Okay, so it's a singularity, demographic singularity. Okay, all humans will either disappear altogether, or or something will happen on that date. And it turns out it was his birthday, so coincided with his birthday, 13th of November. And some people think that because his equation predicted some numbers there, that maybe his equation has some truth to it. And the problem here is that, again, all these people do predictions, and people don't pay attention to them because they see them as like modern-day Nostradamus, where the guy makes a prediction, says, oh, my calculations say on such and such date this will happen. And, people say, give it, treat it with a grain of salt, just a pinch of salt there, says, well, I don't know if to believe that or not, but okay. And nobody pays attention to these people. That's what's happening. People simply ignore them, and they're really blindsided to extinction because of these things, because we have all these astrologers, that's what I call them, and they make predictions on when things are going to happen, especially extinction. Or when we reach a peak population or whatever. Okay, and here I looked up one fellow, and his name is Kenneth Johnson. He's supposedly a demographer, styles himself as such. He's consulted quite a bit by important networks and news outlets and so on. And here you see a really quick note on Johnson says that he was quoted more than 2,000 times, and he was interviewed by all these, programs and so on. And he says, I'm a demographer and an academic. I lay out the numbers. Well, if he lays out the numbers, if that's what demography is, it's not a part of science, okay? Because science does not deal with numbers. Science deals with explanations. Numbers can only describe. Numbers cannot explain. An equation cannot explain absolutely anything. Mathematics is exclusively a descriptive language, okay? So if he thinks that numbers make him a demographer, well, then he's not a scientist, okay? That's all I'm saying. Or we have to redefine what a demographer is in a way that it doesn't involve numbers. But here you can see one of the problems he has. This fellow has an extensive academic background. He's consulted by all these outlets there, and he says one of the big questions is all these births that haven't occurred. Are they just being delayed? Are these women going to have these babies later than they would have otherwise? Or are a lot of these births going to be foregone entirely? In other words, here you have a demographer. He styles himself as an expert. Everybody consults him, and he's not able to answer this quick question, this simple question that you would think all demographers would be able to answer, why women are not having babies. And he doesn't have an answer for it. He has only the question. So you wonder, with all his experience, how come he cannot answer such a fundamental question? You would think that after so many decades, at least maybe centuries, in which demography has been around, you would think that by now we would have an answer to these questions, right? And he doesn't. And it turns out he specializes in rural populations, and he says the following. He says, I'm a demographer, again he's saying that, studying rural America. Great, okay. Now, he states some facts, okay? And again, all these people state them as facts, and in science we do not have facts, okay? Your facts are not my facts or your neighbor's facts, okay? Everybody has different facts. So in science what we have is a statement of the facts. When the prosecutor meets the jury, okay, he doesn't say, look, I've got the facts. The facts are like this, No, he states his version of the facts, and the defense attorney gets to state his version, okay? So what we call him is the statement of the facts and not the facts. But this was, he reads them out like, this is a proven fact, right? And many people probably disagree with him. He may call them ignorant. He said, well, you're ignorant of the facts. But yeah, if different people have different facts or different ideas about the facts or different opinions, we cannot call them facts. He's talking here like if he's got God-given facts, okay? And that's why we don't have that in science. In science, we have statement of the facts, okay? Opinions. In other words, we call them assumptions, okay? It's an assumption. And we concede assumptions in order to understand the theory. And he mentions several assumptions there. He says hundreds of rural counties have fewer people today than they did a century ago, okay? Older rural residents age in place. Young adults continue to leave. Few young women remain to have children, and the rural child population is diminishing, okay? So he's giving you more or less a fact that kind of is like a theory, because he's saying, look, this is the reason child population is shrinking in the country, in the rural areas. Thus exceed births in these counties, producing a downward spiral of population decline. Again, these are just facts. So far, what's he going to explain with all this, right? And then he says 20th century urban population growth has far exceeded that in rural areas. Okay, again, facts. But the problem is, what is he going to use this for? And at the end, he issues what is known as a recommendation, you could say. He's trying to influence the policymakers, the powers that be. Like, you better follow my instructions or my recommendations or else, or this is what's going to happen. You need to create more housing or less housing or more bridges or less roads or whatever because of my data, right? So he says policy makers need to design comprehensive policies that can address the multifaceted challenges rural communities face. Yeah, when you make a recommendation, you're not talking about science, you're talking about religion. That's not part of science. So again, that portion there is not part of demography, if demography is going to be treated as a science, okay? And this is where these people get it mixed up, because they think that by doing some fancy footwork with statistics and getting their facts, their version of the facts, they now are going to influence the powers that be and say, look, you got to listen to me or else this is what's going to happen, right? That's their posture. That's how these people come across. And yeah, people like this fellow, Johnson, he influences people like the President of the United States. Here you have Trump, and he has this idea that, somehow they convinced him or they persuaded him that, the United States does not have enough babies. These piece of news came out lately. They've been on the news, and he says maybe we should, give a baby bonus, some money, $5,000 to give incentive to the women to have children. And I'm sure that a lot of this comes from some demographer who persuaded him or convinced him, or he listened to this person and said, well, maybe you're right, I think you're right. And so this is a recommendation that he's now turning into a policy, right, into something that he's going to implement, perhaps, right, if it's approved maybe by Congress. And here you have one fellow who's certainly influenced him. His name is Elon Musk. And he says he's obsessed with America's falling birth rate. And apparently they ran a poll, and they said, well, he must be the only guy, because a lot of people in general don't give a damn about this thing, about women having children, about the population rate and population increase. And it says the survey of adults show that only 8% say they are very worried, and just 32% say they're worried at all about U.S. birth rates falling. Okay, and 59% say they're not very worried at all, or 30% or not worried at all, 29%. In other words, relatively few people think this is a subject matter that concerns them. Okay, and you say, well, Elon Musk is concerned. Is he right? Or are these people just ignorant? Or why are they dismissing his concerns? And here's another article that puts it in maybe in the right perspective. He's trying to, I guess, populate the United States all by himself. He had 14 kids, apparently, right? And he says he welcomed 6 children with 1 wife. He praised the contribution to the population crisis. And he says a collapsing birth rate is the biggest danger civilization faces by far. There are not enough people in the world. And there's other people who say there's too many people in the world. We should have stopped a long time ago, maybe at 2 billion or 1 billion, and we have too many people. He's saying, no, we don't have enough people. And so who's right? Are these just opinions or what? And he expressed concern for civilization if people don't have large families. Okay, and the question is, is he right? Is he doing the right thing by saying we should go out there and have kids? Is this what's going to save the world from some kind of economic collapse? And he says low birth rate is killing, is going to kill or is a risk to civilization. If people don't have more children, civilization is going to crumble. It's going to go down the drain. So he's saying a lot of the future depends on whether women, men in general, couples really, have children. Especially women, they're the ones who have the children. And the question is he in the right century? Okay, who's counseling him? Is it some demographers that are whispering in his ears? Where does he get this information? Surely he consulted some demographers, and some of them told him what he's saying out there. It's not like, he's in isolation. It's not like he came up with all of this all on his own. Surely he has consulted demographers, and some of them, or many of them, or whatever, or the ones that he trusts the most, convince them that you got to do something about the population. Okay? What's interesting is that they want to offer money to women to have children, $5,000, right? Maybe some women might accept the deal. And here we have good old Putin, and he's got the same problem over there in Russia. He's offering 1,200, a little bit less, 4 times less. But he's offering money to women to have children also. He wants a baby boom. He's saying Russia has a problem with population growth. In fact, they're in negative population growth for a long time, and they don't have as much immigration as the United States. And so the question is right now, population is declining in Russia, and that's a problem for the Ruskies, right? And here you have another fellow who's worried about that. His name is Xi in China, and he's worried about also the fact that women are not having children. And you see China. I mean, China is overflowing with people, aren't they? What is it? 1.3, 1.4 billion people. And he wants more people. I mean, what's going on here? I mean, shouldn't they start cutting back instead of pushing forward? Shouldn't they re-implement, the one child per family deal? And so we have a problem here because all these great leaders of big countries, right? Populous countries, they're all worried about population decline or the fact that women are not having children. And you would say, is Musk right? I mean, should we have more children? How's that going to help the economy, right? This is what's behind this whole thing, right? And here you have a country, India, which is ready to become the most populous country in the world. And they're not worried about population. They're still growing. But as you can see, if you look at the numbers there, the years, right? Those are the curves. And the curves means at some point they will also be hitting asymptote and start dropping back. Okay, they're going to be losing population. So what's going on here? If every country, including India, is going to fall backwards at some point, we seem to have a problem, right? I mean, maybe it is a problem, maybe it's not. Some people will say, "Hey, good riddance. We need fewer people in the world." Do we? I mean, does that not cause some kind of economic impact on the global economy, right? Is there going to be some negative economic process because people are not having people? Okay? And here you can see the numbers, and this is what, I don't know if Musk or Putin or Xi or any of these people saw this, but they really should get this under their belt, right? 1963 was the last time we had 2.2 to 2.3, I think it was, growth rate for the whole planet. This is for the world population, right? And today, where that red line ends, around 2020, 2025, thereabouts, we're at 1.0. So we have dropped our population growth rate significantly. We cut it by half at least. And the green line, that's my line, okay? It's not a projected line or anything like that. But if you read, a lot of these demographers, they do their calculations, and they say by mid-century we're going to reach what is known as zero population growth, ZPG. And so that's why I drew that line at zero at 2050, okay? And more or less a straight line or somewhat curved there, geodesic. Okay, so by mid-century, if the projections are correct, again, this is just statistic, people doing numbers and say, well, we project that by the year 2050, thereabouts, mid-century, we're going to reach zero population growth for the entire planet. One person is born, one person dies. Okay, so it's like they compensate each other. And after that, as you saw the India curve, it goes downwards, right? And the question is, where does that lead? Assuming it continues, right? Does it lead to extinction? Does it go to zero, not growth, but zero population? Extinction, right? That's the question. And we need to figure out, in this case, if extinction is part of demography. Does that conduce to extinction? And what we say here, is that we have two mechanisms for extinction. One of them is the inversion of the population pyramid, which is how background extinctions happen. And the other one's the mass extinction, which has nothing to do with asteroids, with volcanic activity, climate change, methane coming out of, in plumes out of the ground, or any of those catastrophic agents that all these so-called paleontologists have come up with over the years. They haven't figured out extinction. That's the point. And it's important to know how the mechanism of extinction, of a background extinction where a single species is wiped out by Mother Nature, and another one where a whole you could say order. Really, it's I call it a food chain, right? Disappears. And so here are the suggestions here of how extinction happens. We have the overturning of the demographic pyramid, and that's when a single species disappears. Why does it disappear? Because their population pyramid overturns. You have more and more older and fewer younger members in that population. That's one issue. And the other issue is they lose, after thousands, perhaps millions of years, they lose their genetic diversity. So those two cause a double whammy and kills the species. That's for background extinction. And for the mass extinction, we have what is called the ecological pyramid overturn. And what happens there, again, all the animals depend on food, they find out there, especially, we can understand this with animals that are in the wild in the past, right before humans came around. And you can imagine if the population pyramid inverts, right, for the plants, guess what happens to the animals that depended on that source of food? Well, they go down with it. Okay, so the green one up there, that's primarily, I use it, or you can use it for humans or animals as well, but it's a good one for plants. That's why I always keep it in green, because if you have the population pyramid overturned for plants, after millions of years, their population pyramid overturns because more and more plants of those types become older and older and older, and they lose their genetic diversity. At some point, they have an implosion, whereas at the same time, another plants are taking over the land and they wipe them out. So these islands shrink until they disappear, and the animals that depended on that source of food cannot change overnight to the other source of food. That's the issue. That's the theory, okay? And so there you have the mechanism for extinction. And so the question is, how does demography fit in with that? I mean, now if we have a mechanism for extinction, now we can talk about demographic trends and so on and relate it to these mechanisms of extinction. Especially, the population pyramid overturned, since our population the global population for humans has overturned in 1963, that's 60 years ago at least, right? And we can't overturn that ever again. We cannot reverse that process. As intelligent as humans are, we cannot reverse it. Okay, and why? And part of it has to do, or a great part of it has to do with the fact that what this fellow Johnson explained, which he didn't listen to his own words, okay? The fact that we moved from the country to the city. We moved from rural areas to urban areas. You can't have children in urban areas. They're prohibited. It's against the law. You can't have 10 children in an apartment. It's just that simple. I mean, in the country, you had all this space, and people in the old days, especially, look at biblical days. Why did Israel have 12 boys and a girl? Well, because he wanted to, cover the land. He wanted to create a nation. He wanted his seed to multiply. It was an empire-building mentality. Nobody thinks like that these days. It's totally in reverse. Now we're all concentrated in the cities, and in that city, in that environment, there are not only economic problems, that prevent, lots of people from having children, but then you have, social problems. You have cultural differences from, when we lived in the country. So a lot of things change, economics, social ways of thinking, etc. All that helps to prevent people from having children in the cities. You cannot have children in the cities. It's forbidden by law. That's the way I put it. Okay, and here you see, I'm going to show you a little bit of evidence, little religion to persuade you, just so you see the facts, or my version of the facts. It's called an assumption. Okay, you can take it any way you want, but here it is. You want to factor this maybe in your considerations. Here it is. You had these animals in the past. Why did they disappear? Well, they didn't disappear because there was some kind of catastrophe, some extraterrestrial impact or volcanic activity or climate change. None of those. What happened here was the food disappeared underneath their feet. That's what happened. After millions of years, you can see here, for example, in the first one there, the Devonian and the Carboniferous, you had non-vascular and early vascular plants. That's what the amphibians ate because there was nothing else to eat. Those were the only foods for the herbivores, and the carnivores, preyed on the herbivores. When those types of plants started dying out, so did these animals. They became fewer and fewer, and at some point they disappeared. They were replaced by whom? Well, the plants were replaced by seed ferns primarily, especially at the beginning of the Permian. And the animals that came out of that were animals that were small in the days of the amphibians. Now they're big, and they became the synapsids, or mammal-like reptiles, you could say. That lasted to about 252, really, the end of the Permian, and the Triassic started. And what disappeared there? Well, the glossopterids. That's what these animals ate. They were the seed ferns of those days. That was the only food available almost everywhere. And when the glossopterids disappeared, well, guess what? So did the Permian mammal-like reptiles. What replaced them were the archosaurs of the Triassic. What happened to them? Well, they disappeared when their source of food disappeared, which were another type of seed ferns, the dicrodiums primarily, and that gave way to the dinosaurs of the Jurassic and Cretaceous and so on down the line. What disappeared at the end of the Cretaceous, the famous extinction? Well, again, primarily the conifers. Okay, that's what disappeared. And here we have, here's the graph that more or less shows that, a 4-year study known as the Cretaceous Terrestrial Revolution. And there it is. You can see what happened after the Jurassic. The angiosperms started taking over the land. Angiosperms are the flowering plants. That's what we eat today. Mammals eat that. Dinosaurs did not eat angiosperms. What they ate were primarily conifers because they radiated with the conifers. They didn't eat ferns because that was the food of the mammal-like reptiles. Okay, so they didn't grow really with ferns. Maybe there was one dinosaur here or there that may have carved a niche in ferns, but primarily they ate all kinds of conifers, among them cycads, ginkgos, and other conifers of different kinds. But you can see what's happening here. The angiosperms started crowding out the land, and why? Because the others were dying. The others were old, they had been around for too long, and it was time for the conifers to give way. And today we only have conifers in the northern and very southern hemispheres, and everywhere else we have angiosperms. Okay, partly because we sow them ourselves, but partly because that was the natural fight between these plants. The conifers gave way to the angiosperms, which were more vibrant plants. But you can see what's happening. As soon as the Cretaceous gets to around 65 million years ago, you have lots of angiosperms everywhere, and the conifers are dying. The islands are disappearing. The islands on which the dinosaurs depended were disappearing, and at some point it was just a critical ratio between animals and plants, and they disappeared. So we don't need any asteroids or any of those things. In fact, here you have an asteroid. This is the way they picture it, okay? They show that the land was covered with fire all over, okay? And they burned all these animals, these dinosaurs. The whole planet was on fire. Oh yeah, burned everything, even plants, right? After the asteroids hit. Absolute nonsense. This is poppycock. Whoever came up with this has no idea what he's talking about. That's the reality. Okay, you can't say that these animals disappeared because there was a big fire all over the earth. Okay, in fact, there's no evidence that all plants and animals disappeared. So where did he get this? These theories shouldn't even reach. They shouldn't even be peer reviewed, and they should not reach the scientific literature. They have no place in the scientific literature. Turns out, to kill more animals, they put a tsunami. They say, oh, by the way, the asteroid created this tsunami that flooded the land and just drowned out everything. And again, these catastrophic mechanisms are irrational. none of this ever happened. And so again, these people are inventing stuff that doesn't exist. Fire and water and brimstone, and then you have the also the fact that all the dust covered the earth and the sunlight didn't come in, and so you have this what is it? It's called not an impact winter, they call it. There's an impact by the asteroid, turns into all this dust that covers the planet for several years and killed everything. No such monster ever happened. It wasn't like that at all. It has nothing to do with how the animals, especially the dinosaurs, disappeared. Okay, so those are the mechanisms we propose here. We're saying, the overturning of the population pyramid for background extinction, single species, right? And the overturning of the ecological pyramid for mass extinctions. And so, when you look at it in those terms, you understand that we're never going to have kids again. It's never going to happen. We're never going to be able to overturn the population growth rate. It's impossible. Once you turn that corner, you can't reverse that process. Why? Because we went to the cities. The only way to change that, if you could muster, any politician can muster the force, the power, the authority, would have to move everybody back to the country, right? For what for? Are they going to work with their hands now, where we can replace them with machinery? So man's not going to replace machinery in the country anymore. Machinery has pushed man out of the country, and manufacturing is dying, because it's only becoming a smaller and smaller percentage of the economic world, especially of what used to be called industrial nations. They're no longer industrial nations. Now they're service nations. There's no more industry. The industry is being shifted to places where it's cheaper and you're producing more with less, with fewer people working in manufacturing. Everybody's moving into services. And within services, we're creating this new world, which is internet services. So we're moving from hand services, landscaping or barbering or stuff like that. And we're moving from there to what? We're moving to internet services. There's no hands involved there, so except typing on the typewriter, right, on the keyboard. Okay, so it's funny when one of the people here from the government says factory gigs are the great jobs of the future. That Gen Z could work in for the rest of their life, and so could their grandkids. You got to remember these plants, all these automated arms and stuff, they need to be fixed. They all need a technician to fix them. So he thinks they're going to try to put everybody to work, oiling, the the robots, the R2-D2s. Robots are already starting to work side by side with humans on factory floors, and it's causing panic among workers that the tech will eventually steal their jobs. Exactly, that's what's happening. But Lutnick snubbed that notion, arguing people will always be needed to repair the robots. Yeah, I don't think you can put 8 billion people to work on robots. I don't think we need that many people to oil the robots. In fact, you can use other robots to oil and repair other robots. So you don't need humans for that either. So no, robots and AI and all this stuff that's going on, that's going to take away jobs. In fact, I heard of a case, a fellow who works in programming. He has, says like there's 7 workers that do internet stuff, programming stuff. And he says what it used to take him a whole week, now he can do in one day because of the AI. He just, just subcontracts to the AI, and the AI comes up with the results in one day. And so if there's 7 guys and you can do the job of 5 days in one day, well, you're going to get rid of some people. You won't need 7 people to do the same kind of work. You can do it maybe with 2 or 3. And so there's going to be job losses, without a doubt. And so that's what efficiency is all about, the fact that you can produce more with less, cheaper, right? And the worst thing that, or the worst cost for a employer is labor. So they don't want to pay labor if they can avoid it, especially, vacation, sick time, all that stuff. Hey, they can avoid all that with robots. completely. Okay, so what's the issue? Here's the economic modes through the ages as I see it. And here you see we were hunter-gatherers for most of our existence, maybe 200 to 300,000 years, maybe 10,000, 15,000 years, primarily in the Neolithic. We were farmers. About 200, 300 years ago, we got into manufacturing, got people out of farming. They came to the cities. We started building towns. And we gradually started evacuating the country and replacing man with machine. And today we're replacing manufacturing with services. First with labor-intensive services, hand services, hands-on. And today, maybe 10, 15, 20 years now, we're replacing that with internet services. Okay, so, and what is internet services? It's unemployment. That's what it is. It's another word for unemployment. What is a person who works with a computer? He's an unemployed person. He's not producing anything really. He's producing a service, and service primarily today is for entertainment, right? And commercials, ads, right? That's not producing anything, and it kind of secondary production when you produce something with a manufacturing people, but or when you build roads or houses or whatever. Otherwise, just singing, that's a service, right? You sing, you're not producing anything. A singer is an unemployed person, and so is a guy who does programming. So is all these people who work with computers, which is, the line item that is growing in the economics of the world. So, yeah, right now we're headed towards a point where, at some point the global economy has to collapse. It will collapse. It's not a question of if, it's just a question of when. And it's going to collapse because at some point, there will be fewer and fewer jobs, meaningful jobs. People will not be able to make real money, will not be able to pay their rent or make it to the end of the month. At some point, nobody will accept money. Money is what's going to disappear as a medium of exchange. When that happens, when we do not accept money anymore, and people say, well, is that possible, Bill? I'm not going to accept money? Well, I'll pay for your car. How's this? And I'll pay with Vietnamese money. Will you accept it? You say, no, I don't want Vietnamese money. What can I do with that? Well, that's the point. The point is, money is not money. There's stuff which we consider money and other stuff which we don't consider money. So there's a lot of money out there, and I'm sure the Vietnamese government backs its own money, it's backed by their gold or whatever. But you won't accept Vietnamese money for sure. And so money is not always money. Okay, some people will accept stuff and others won't. Some people may want bartering, accept some good for another good or service for a good or something along those lines. But at some point, you can't run the global economy anymore on bartering. But at some point, the global economy will collapse. Not a question of when, if. It's a question of when. When it happens, when the global economy collapses, when money is no more, when we don't trust in God anymore, like the bill says, then we're in trouble because the people who produce food, the companies that produce food, will have no incentive to produce food for or distribute them to the cities anymore. They will have no incentive. So, so all those demographers, they should really focus a little more on the mechanisms of extinction and then build their curves related to that. But what they do, they just do statistics on past data, and they just project it. They extrapolate it and say, well, if for the last few years we've been declining, the population's been declining for such and such reasons, then we can project it and say by the year 2030 or 2040, this is going to be the population. And you can't really do that because there's a lot of qualitative stuff going on there that can derail all those calculations. And again, we need to understand what causes extinction, and then based on that, then we can go back and do demographics, especially demographic curves. Okay, so let's move on to the main subject of the day, and that's going to be, flavors. We talked a little bit about that the other day, some of the flavors. And I'm going to start with waves. It's important to start with waves because we need to get the wave out of the wave. We wave it away. We wave the wave away, okay? Here it is. Let's start real quick with a history of the wave. Okay, and here it is. They had the ether all the way to the almost all throughout the 19th century, and in 1887, Michelson and Morley they convinced mathematicians who call themselves physicists, right, that the ether didn't exist, or a lot of them became convinced, right? And so what was it that was waving if not the ether? Because that's what they thought was what the wave was. Light, right, was a waving of the ether. And these guys apparently proved to many of them, to the many mathematicians, that there is no ether. So then what is it that was waving? And so rather than answer the question, what they did, they looked for other outlets, and one of them was that they started making calculations based on the speed of light and time. They use time and speed of light, and they say, oh, what's happening is we have a shrinking of the distance, or distance traveled, or length, or whatever, right? Because for them, there's no difference. And so they started going in a different direction. Instead of saying, instead of accepting that they didn't know what was waving, they said, well, it's still what's waving is the ether, but we can explain the results, the null results of the Michelson-Morley experiments, right? And they did more than one. Okay, so what happened? By the turn of the century, you had these milestones here. You have Max Planck show that light comes in discrete bundles of energy, the famous quantum, right? That's when quantum really started, you could say. Maybe not the name, but surely, slowly but surely, the bundle of energy became part of mathematical physics. Okay, that's when it started. Einstein, he demonstrated the Planck quantum could be used to simulate the photoelectric effect. You had this bundle of energy that hit an electron and kicked it out of its atomic orbit, or whatever, because they didn't have an orbit, they didn't have a notion of that yet, but kicked an electron, and the electron started flowing, and that was electricity. So that's how they explained the photoelectric effect. He won the Nobel Prize in 1921 for explaining the photoelectric effect based on the quantum. Okay, so throughout the 20th century, especially the first quarter, right, what happened was that they had these two versions, the wave and the particle. Especially when Louis de Broglie, he came up with the idea that particles also have wave-like behavior, especially the electrons. So not only was it light, but also the electrons and maybe other particles that had wave-like properties. And because of that, they started saying, okay, we're going to have this duality. Particles, no matter whether they're photons, electrons, or eventually neutrons and protons, they all have wave-like behavior as well. Okay, so it's not only a particle, it's a wave. We have the wave-particle duality. And we have this all the way to today. Nothing has changed. Everybody believes in wave-particle duality, and mathematicians like it because it allows them to cover all the bases. They can explain anything with that, because if you have a malleable hypothesis, a malleable assumption, right? Well, you can use it for this, or you can use it for that. And when you want to explain something that relates to wave, you use the wave. And when you want to explain something with particles, you use the particles. Turns out that the bundle of energy is not a particle, because energy is not a particle. Energy is a concept. So what is a particle? Well, we discussed that last time. A particle is not a particle. It's not the famous, Newtonian corpuscle. It's not a little ball, a little bead. Quantum just means, quantum particle means number. That's all it is. It's a value. What they're accelerating are values. They're just going to talk about, what they're accelerating in terms of energy or mass or whatever, not in terms of balls. And so they don't have physical interpretations for all these things. That's the issue. Okay. And to this day, we have no physical interpretations from the entire mathematical establishment, where they simulate it with real balls. They simulate it with a ball. They'll put a point, they'll put a little ball, and then they say, oh, don't mind the ball. That's just because I need to put something on the screen. But if you want to really understand it, you got to come to mathematics, and we're going to show you, the numbers, the equations. Okay, that's what they're dealing with. Okay, but what's the problem with the wave? If there is no such thing as wave, why? Why is it an irrational proposal? Because that's what it is. It's an irrational proposal. And there you see it, okay? Wave is made out of what? Vectors. Actually two fields. What's a field? You see it there at the bottom. It's a value at each point in space. So field means values, many values around something, and those we're talking about numbers followed by units, predefined units, standards that we created. And so we have these two fields, which are just a bunch of numbers with units, and each one of those fields is made out of vectors. What are vectors? Well, it's magnitude and direction. And actually, it doesn't even have direction. That's the issue. That's wrong too. And one of the things that you'll see with it is they put it in motion. And here, let me see it. I see if I can put it up there. And so they have this. They have these vectors, and they're moving. It's scary stuff. You have all these mathematical concepts, and they're moving. And that's how they portray them. And so what are we supposed to think about this? You're talking about a concept, a bunch of numbers that are moving. That's what you're staring at. Okay, so yeah, it's a problem. And, a wave is not a thing. What it is an abstract concept made out of fields, which are concepts, and the fields are made out of vectors, which are concepts. And it turns out the vectors are weird because, vector of math is not the vector of physics. And we have to make a distinction there just in case because, in physics we use vectors, but it's qualitative only. Vector is depth, breadth, and elevation. Those are the three vectors of physics, okay, which is motion in three mutually perpendicular directions. That's what a vector is for the purposes of physics. It's qualitative only. And in math, they don't have vectors. They don't have dimensions, and they don't have coordinates. What they have in math is magnitude. And they're talking about no orthogonality or direction because these are qualitative concepts that don't belong in math. They're just talking about number lines that have only magnitude. And it's so weird because they put, a line with an arrow. And the arrow is not direction. Arrow shows that numbers are increasing. That's very different than physical direction, like, that direction. That's not what that arrow means. But that's what's so misleading about that arrow because people think it has to do with direction. In fact, they define a vector as magnitude and direction. No, a mathematical vector does not have direction. It only has magnitude. And it takes a while for people to catch on to that argument. Okay? So I'll let you roost on that. Okay, so what's the issue? Here you have Stephen Hawking. He confirms what I just said. Okay, Stephen Hawking, he was a so-called mathematician who called himself a physicist. Says, in relativity, there is no real distinction between the space and time coordinates, just as there is no real difference between any two space coordinates. Right, because they're talking about number lines. They're not talking about coordinates, vectors, or dimensions. So space-time is not four-dimensional. Space-time is four-number-lined. Only has number lines. And here you see an example. We had used to have this. The meter used to be a solid rod of platinum, and this was standard number 27, which became the meter for the United States for many years, all the way to 1960. If you wanted to know what a meter looked like or what it measured, well, you had to measure it against that one, which was the standard for so many years, 100 years, right? And that was replaced in 1960, and you say, well, what was it replaced with? And this is where you got to get a beer or something. They replaced it with motion. Yeah, just like I'm saying. They replaced it with motion. So you had this stick, right? Metal stick, right? And they replaced that with the unrolling of the measuring tape. What was it that they replaced it with? Well, they replaced it with this. They replaced it with the meter, the length of the path traveled by light in a vacuum during a time interval of 70 seconds, right? Which is the inverse of the speed of light. Okay, so why? Because length is a measure of distance in the religion of math. Okay, they don't see a difference between length, distance, or distance traveled. For them, it's all the same because they're going to have to unroll the measuring tape irrespective of which of these qualitative, words, right? Especially length and distance, irrespective of what they really mean. Length belongs to physics and distance belongs to physics. Neither one of those two words belong to math. The only one that belongs to math is the distance traveled, which is the unrolling of the tip of a measuring tape, or counting tiles, if you will. You measure a tile, say 1 meter, that's going to be your standard. You use 10 tiles, that's 10 meters. So you counted tiles. It's you laid tiles or you unrolled a measuring tape. That's what it is. But the funny part is it says light in a vacuum. Turns out in the religion of math, math phys, right? There is no such thing as vacuum. You look up and it says space devoid of matter. All right, that's the definition of vacuum, but it's not, because vacuum, any space in which the pressure is considerably lower than atmospheric pressure. In other words, vacuum always has something in it. That's what they say. That's what people are told to repeat like a parrot, right? And in QED and QCD, right, you have this vacuum. It says vacuum fluctuations that produce transient virtual particles. So whenever you don't have real particle, you have all these virtual particles popping from the void. So there is no such thing as vacuum in mathematical physics, okay? And they have these vacuum fluctuations. What is it? The temporary random change in the amount of energy in a point of space, okay? And so they follow good old Aristotle there, who said, nature abhors a vacuum. Yeah, there is no such thing as vacuum in the religion of math, and they never established the difference between length, distance, and distance traveled. So here we educate them and show them what the difference is, just for people to know. Distance, this is according to them, right, the mathematicians, is a numerical measurement of how apart objects or points are. Absolutely not. Okay, distance is separation. That's what it is, a qualitative concept, okay? And then they say in physics, actually mathematics, right? Distance may refer to what? A physical length. No, not at all. Not in science, not in physics. In physics, what you see at the bottom. Distance is what lies between lengths. Length is what an object has. Distance is what an object does not have. Distance is the separation between 2 points. It could be within the length, but now you're unrolling the measuring tape if you're going to do distance traveled. Otherwise, this is just separation, okay, between objects. Okay, so distance lies between lengths. Once you learn that, you get it. You're all set, right? What mathematicians use is distance traveled. They don't use distance. They don't use length at all. They just unroll the measuring tape. They look at meters, feet, inches, whatever. Those are unrolling the measuring tape. They're interested in numbers. They're not interested in qualitative notions at all. And that's part of the problem. Okay, but what's the issue with a wave? The issue is that we have this wave, and we have to determine, is there a physical object called a wave? And they say, well, the wave, extends infinitely, or it travels. And what are you talking? What do you mean the wave extends or wave travels? And here you see what they have to answer. This is what they have to answer. Okay, here it is. Watch it. There you see it. Either it extends from the Andromeda Galaxy all the way to Earth uninterruptedly, or it travels as a little sailboat from there to here. Which is it? Does it travel or does it extend? That's what they have to answer. Where does the wave begin? Where does the wave end? And again, what is it made out of? Is it made out of vectors? And so all these questions are stuff that they have to answer, and they never do. They never tell you whether it extends or travels. Okay, and this is the only question that a mathematician needs to answer. Who proposes the wave? And the problem with the wave, again, is that you will not find it anywhere in quantum mechanics in the standard model. Right? You would think that if particles have duality, right? They are both waves and particles. Well, where's the wave chart? I've always seen the standard model, which is particle, a bunch of balls, okay, and looks more or less like this. Okay, do you see any wave there? It looks like all particles, right? And so where does the wave come in here? Why don't they put a chart like this for waves? And again, it wouldn't make any sense in great measure, because a wave is just a bunch of vectors. It's just numbers. And so they use that concept, but they turn it into a physical object. They say, the wave moves or travels or whatever. Okay, so they replaced the particle with the waves with particles. That's essentially what's happened. That's why quantum has survived all these years. And they give lip service to the waves. That's what's happening. Quantum uses wave only to justify why discrete particle is everywhere. So if they want to show that the particle is everywhere, they bring in the field concept, which, you have two fields make up a wave, electromagnetic wave. And so now you can fill the whole space. The wave is everywhere. And, what kind of explanation is that? That's like God being everywhere. God is everything. Yeah, that's a great explanation. I learned a lot with that. And the wave is everything as well. It's everywhere. And so you haven't explained anything. You either use the particle or you use the wave. And so they have this particle collapse, the wave function collapse, and they give a lot of interpretations to that as well. But essentially they're saying, the reason you can measure a particle is that the moment you touch it with your probe or whatever, that's when the wave collapses. So we have the wave that extends throughout the universe, and suddenly it collapses to a point right there where you put the stick. Yeah, tell me about it. Okay, and otherwise quantum mechanics always use the particle, and that's all you'll see in the standard model. Okay, so this is the problem. The problem is they don't have any physical interpretations for any of this, because again, what they're using is the notion of the particle to explain almost everything, and they're going to be explaining all these things in quantum with particles. They only bring the wave when they have to explain, why the particle is everywhere, or at two places at once, or whatever. And so here we have a lot of what has to do with the subject matter today, which is flavor. How do we end up with this? Well, they were looking at cloud chambers. First, they were looking at bubble chambers, later cloud chambers, which is just an environment of some molecules there, some kind of gas or whatever. And they're going to look at traces of particles, because now they're not going to invoke the wave. They're going to invoke particles. They're going to say, oh, we have a discrete particle, a little ball, right? Remember, it was a particle, just a number, right? Well, that number somehow becomes a little ball, because now that ball is going to go through this environment, this gaseous environment. Okay, and so here you see something a visitor sent me. He said, look, here you see all these traces, okay, and you see some of the traces there. And we're going to look at the one that's in the circle there, okay? There are other traces there you'll see everywhere, some very thin, some very thick, okay? But we're going to look at that one there, okay? And let's look at it in a little more detail here. Let me show you this one. Okay, and here you see it. This is what it looks like up close. Okay, so wait for it to start again. Here it goes. So there you'll see the streak now. Okay, that's what happened, right? But what is this? Well, you see that it's a curlicue as it gets bigger and bigger. And here I took one of the shots from that. Okay, there it is. Here, let me see if I can put it up here. Okay, that's what it looks like. Looks like a little curlicue. And the question is, what are we staring at? Are we staring at a particle that's going around in circles many times in a split second? Is that what we're looking at? And the question is, if this particle is traveling close to the speed of light, how does it turn those corners so fast? I mean, is this a particle? It looks more like a bed spring if you ask me, right? But the question is, can that be a particle? Is it possible that it's a particle? And they say these big ones, these fat ones, right, is a alpha particle. And an alpha particle essentially is a helium atom. Looks more or less like that, okay? That's what an alpha particle is. It's charged because the two protons allegedly lost their electrons, okay? So it's doubly charged, and they call that an alpha particle. It's essentially a helium atom that's lost 2 electrons. That's the bottom line, okay? So that's what they say these thick lines are. The thick line simply represents an alpha particle, a helium atom without 2 electrons, just going right through, in other words, an ion, doubly ionized, went right through this gaseous environment, right? And we have a problem with that. Why? Because whether you use the magnetic or the electric versions, in other words, electricity or magnetism, you don't end up with particles. Okay, here's the idea. If that's the quantum atom, in other words, if an atom is an electron that somehow is to the side of the proton, rolling around or jumping around erratically between energy levels, between orbitals, what keeps it bound to the proton? That's the first question. Why doesn't it fly away? That's one part of it. But then you have electricity on the bottom. What is electricity? Well, electricity, according to everybody out there, is the flow of electron beads from one atom to another. Like one atom leaves a hole in the other. When an electron leaves the atom, goes to another atom and leaves a hole, and another electron occupies that hole. And so the flow of all these electron beads, actually charges, numbers, values, right? That's what they say electricity is. Okay, so they think it's the flow of balls. That's how it's illustrated. That's how it's explained. So there should be no questions about that. That's what electricians learn, right? And yeah, you can't have that because obviously, how are you going to explain why the electron moves? Why does it jump to another atom? Which one goes first? Is it the one that leaves the hole, or is it the one that occupies a hole? And again, if you're going to go with all this flow of electron beads, you're going to have to consider them beads, and you can't say that it's a value. It's just a number. Okay, so what are we talking about? And here you see it. One of the big problems with quantum mechanics is their version of electricity. Imagine you have a vacuum chamber, right? You're going to send electricity across that chamber. Well, if you have atoms there, you can imagine best case scenario, right? Even though it's not a good explanation, but at least you have some explanation saying, well, the electrons are going from atom to atom all the way from one side to the other side, right? No problem there. I mean, more or less, right? But now they've taken away the atoms. They say they can flow electron beads without the atoms. Which is what's happening in those cloud chambers. They're saying an electron and a positron, they're separate from their atoms. They're just flying around, all these electrons just flying around, loose. And so they don't need an atom anymore. So now we don't have this electricity version, which is, the electron going from atom to atom. Now the electron doesn't need the atom anymore. It flows all by itself, a bunch of electrons just flowing little beads that have no size, supposedly, right? They're not really balls. What they are is charges, meaning 1.6 times 10 to the minus 19 coulombs. That's what's flowing, numbers. What does that mean? What are we talking about? What's happening physically? That's what we want to understand. And you'll never understand that from quantum mechanics. You'll never get an answer to that. And under the rope model, we have a more rational, hopefully a more rational version of electricity instead of the flow of particles, whether from atom to atom or electrons flowing all by themselves or charges flowing. Now what you have is all these molecules really, but we simulate it with atoms, hydrogen atoms. They're all blended, okay? They're all merged, and they form a continuous string, okay? And so they're twirling around the threads, which form the magnetic field, which runs coincidentally 90 degrees to the flow of electricity, right? So we have this torsion going on of merged electron shells, and that is electricity. That's why it's instantaneous. That's why one pole of, when you have positive and negative poles, really, feel them instantaneously. Because what we're talking about is clockwise and counterclockwise rotation of this whole string of merged atoms or molecules. So it's a different model than what they propose. And if you have a continuous string of molecules, then you can explain some of those curlicues, you can explain the lines, all that. You can explain all that. But to say that there's a little particle that's going through, first it doesn't show that, because you would be able to visualize at some point, just one particle at one location. That's not what we see. We see a whole streak. And it also disappears as an entire streak. That's one issue. But even so, how do you explain particle? I mean, the electron loose? Is the alpha particle loose? What is the charge? Missing an electron? Did you remove the electron from the alpha particle from the helium atom? Did you remove a little bead? Is that what's happening? So unless you can explain that first, you can't say that those are particles. Okay, that's the issue. Okay, so where did he go from that? Well, we explained some of that in the past. We said in the past 2 weeks, really. How did they come up with all these subcategories? Originally, we had, the electron, then we went with a proton. We more or less conceptualized the atom as a planetary model of the atom, right? And from there, they went even further. They started creating quarks. And why did they create quarks? Well, again, very quickly. We talked about this in the past 2 weeks, so we don't need to go over it in fine detail. But essentially, you had 2 plus 2/3 quarks, which is 4/3, minus a 1/3, which is the down quark, and you have 4/3 minus 1/3, you get 1. That was the charge on the proton. That explains why the proton has a charge of 1. Why does the neutron have 0 charge? Because of the opposite. It has 2 down quarks. Each one is negative 1/3. That's negative 2/3. Plus a 1 up quark. That's 2/3. You get 0. So it's a mathematical contraption, a mathematical system that they created, right? That's all it is. There are no such things as quarks. This was a mathematical contraption to try to explain why the proton has charge and the neutron doesn't. And what they can't explain with the same structure, the same scheme, is the electron. I mean, how many quarks does an electron have to get a negative 1.6 times 10 to the minus 19 coulombs? And of course they say, well, no, that one just has it. There's no scheme for that one based on quarks. Okay, because if you're going to explain the proton and neutron, you might as well explain the electron, and you can't, not with quarks. Okay, because you would need to do it kind of in reverse to explain why the how many negative down quarks, negative 1/3 quarks does an electron have? 3 of them, 3 negative down quarks to get a negative 1/3, negative 1 charge, right? So again, this is just mathematical gibberish. That's all it is. It has nothing to do with reality. Okay, so here we have they had to explain in addition to what's inside, the neutron and the proton, the fact that one is positive, have positive 1 charge, the other one has no charge. The mathematicians had to explain why the protons, if they are both positive, they don't repel each other away. And we talked about that last couple of weeks. Here it is. Essentially, the protons would push each other away, but they have this strong nuclear force, right, that overcomes the proton repulsion. And so they produce this pull between protons by push. And what's pushing? The pions. What are pions? Well, pions are a mixture of gluons and quarks. Okay? So they build these pions, and the pions then somehow push the protons from the outside inwards. That's what keeps them inside the nucleus. That's what they had to invent. So they had to invent pions and muons and all these other categories because they had to explain, mathematically, right? Because this is all mathematics. Really. Why doesn't the proton reject another proton? Why doesn't the nucleus of the atom, the center, why doesn't it fly apart? They couldn't explain that. Okay, but then they had to explain something else, and that was beta decay. Okay, and they had this thing that they had to invent was the quantum flavor dynamics, QFD. So we have quantum chromodynamics, quantum field theory, and this is quantum flavor dynamics. Okay? They have to invent all these categories, subcategories, in order to explain different aspects. It just kept getting more and more complicated. Okay, so it has here the reason QFD was invented for what? Need to explain the behavior of particles during weak interactions. What's a weak interaction? A force responsible for what? Radioactive decay. Okay, so they had to explain this force. And they said, well, we can't violate Pauli's exclusion principle, meaning that no two particles can have the same state. So in order to avoid the Pauli exclusion principle, they had to create all these subcategories called flavors and quarks and so on. They created all these inexistent particles. And then they say they observed them, when they looked at their cloud chambers and also at their colliders. Why? Because they see something, they see a trace, and they say, oh, that's a trace of a particle. Well, how do you know it's a trace of a particle if you don't know if it's a particle to begin with? I mean, before you can talk about the trace of a particle, show me the particle. Show me how it fits into the atom, or in the case of the photon, light. Explain, or gravity. I mean, explain it with a graviton. I mean, can you explain that? And they can't. Obviously, they can't. So they can't justify the particle, and whenever they're in trouble, they just convert it into a wave and get away with that. So it's like, you never win with them, and they always have answers to cover all these unanswered questions. And it says, weak interaction can cause particles to change their flavor. So it turns out, let me get back in here for a second. Turns out that all these particles, it's not an issue of, in classical mechanics, if you have something hitting something else, you have a dynamic situation where this one moves because something external changed its motion, right? That's not the case here. Here we're talking about, imagine you have a man and a woman, right? And you move your magic wand, right? The flavor or whatever you got there, and suddenly the man converts into a woman and the woman converts into a man. Suddenly, instantaneously. So there's no motion. It's not like the man traveled or moved around. It's like he just morphed into a woman and a woman morphed into a man. That's more or less how you have to look at flavor. It's the conversion, a static conversion of something into something else. Suddenly you have a different mass, you have a different charge. Mass and charge are the ones you're going to play around with for flavor, because flavor is a combination of mass and charge. So, either you have more charge and more mass, or less of both, or more of one and less of the other. They played around with all these numbers in order to create this streak of particles, gazillions of them. Seems like, they called it the particle zoo. Okay? And so here you see it again. A neutron, for example, morphs into a proton and an electron and antineutrino during beta decay, okay? So what do you see there? Well, you see an equation. That's what you see. You see the neutron is equal to P for the proton, right? The electron, and then it's got an antineutrino. And you say, well, why did they have to put the antineutrino? Well, because the neutron weighed a little more than the proton and the electron. And since the proton has the same charge as the electron, when you add them up, they go to zero. That explains why the neutron doesn't have charge, but it doesn't explain why the neutron has a little more mass than the other two combined, and that's when the neutrino came into existence. So they had to invent, in this case, the antineutrino, right? It has mass, but no charge. That's why it's called neutrino or antineutrino, because it's neutral in charge. Okay, so they had to play around with these numbers in order to try to explain the why a neutron does not have charge. But then it says neutrino oscillations and other particle decay processes are explained as flavor change between quarks and leptons. We have a problem because it doesn't explain anything. What they're doing is, there you see an equation, lengthy one, which I cut it because it really was lengthier than that. And what they're doing is they're describing mathematically, and they call those explanations. There is no explanations. All we have is mathematical descriptions and names that they've given these mathematical descriptions, converted them into particles for the purposes of giving you a physical interpretation, and then they deny it at the end of their presentation, saying, oh, by the way, we weren't talking about particles, we were talking about numbers. If you want to really understand, you got to come to our classes in math. Okay, flavors represent distinct types of particles with different masses and charges. That's all it is. Okay, so it's a combination of masses and charges. They call those flavors. Okay, and you have flavors for both, for quarks and for the leptons. Okay, so you have flavor enables particle interaction to be categorized. So all these are just categories. That's all it is. Just little bits and pieces which they had to invent in order to try to explain little pieces of what they observed, which they always assumed were particles. That's where it is. And in those cases, they never say that it's a wave, because see, if it's a wave, it would extend throughout the universe. That's one issue. But then on the other hand, they tell you that light, for example, travels as a wave, always travels as a wave, but only arrives and departs as a particle. Well, then how come this thing is traveling as a particle? So they have all these contradictions. They live with them. They don't question them. They just continue prod on as if nothing. Quark flavors. You got 6 of those, and you got lepton flavors, and 6 of those. And those are just names. They're nothing more than names. Okay, what's interesting is that, the neutrino, the interneutrino is believed to have 0.8 electron volts, and that's a measure of mass. They say it's really energy, right? Electron volts are energy. But since Einstein said that energy is equal to mass times the velocity of light squared, they say, well, they can call that mass. So they don't talk about energy. They say that's the mass of the antineutrino. Neutrino, they have no idea how much it weighs, but they say, well, they calculate it's probably around 0.45. Okay, and so it looks like these two have different weights, masses, energies, whatever you want to call them. Okay, and they're still trying to figure out what the mass of the neutrino and antineutrino are. But it's interesting that they have these different values. How they can come up with this, who knows? It's just a bunch of math that they put out there, and they just spit it out to the public like, in terms of particles, when they have no particles. Okay, so here are the quark flavors. We talked about that a little bit the other day, and among them you find a strange one there in the center, okay, at the bottom. And these are just names again. And what you can see is that all the difference between them are the masses, the electron volts, really. Some are mega electron volts, others are giga electron volts, meaning billions of electron volts, right? And those are the alleged masses of all these so-called particles, right? And again, they're just talking about values. And what they're saying is, that all these things, these particles, differ in mass and some of them in charge. If it's a neutral charge, well, then it's just mass, difference in mass. That's why they're so concerned about measuring the masses of all these particles. It's very important to them, to the mathematicians. Okay, so where did this strange thingy get its name, this strange quark? And one fellow explains, here it is, we'll let him talk. He's really a nobody, but he explains it well, so I thought I'd put him on. Here he goes.
Quarks are weird. They make up some particles that were thought to be fundamental, like protons and neutrons, and one of the quarks is called a strange quark. As many more particles were being discovered, some hadrons decayed quickly through strong interaction, and some decayed slowly through weak interactions. This was very strange, so they called this property the strangeness of a particle.
So all they did was say, it's a strange behavior, so we'll call it strange. So that's where the name came from. Okay, but meanwhile, they had these leptons they had to give, which were the carriers of forces, right? And they had to give them also different flavors. Okay, and so they have the lepton number there. Neutrinos have a lepton number of +1. Well, antineutrinos have a lepton number of -1. They just had to say, well, we have a neutrino and an antineutrino. And how are they different? One's +1, the other one's -1. Whatever that means, right? These are just names. These are numbers assigned to names or names assigned to numbers. The difference in lepton number ensures the conservation of lepton number in particle reactions. Great. Then they have this chirality, and neutrinos are typically left-handed. So it's talking about handedness. Okay, so they had to show how these particles differ also in chirality, which is a physical explanation, because they're talking about whether it's clockwise or counterclockwise, or looking in this direction or looking in that direction. Okay, they're opposites, mirror images of each other. That's got very little to do now with math, right? But then they say, meaning their spin is aligned opposite to the direction of motion. The problem there is that they never define what spin is. They have no idea what spin is. They never defined it in 100 years. They insinuate that it's spinning like a top. Then they clarify that it ain't. It's not spinning like a top. And then they illustrate it and give their entire dissertation as if it were spinning like a top. And so we don't have any idea. Is spin spin or is spin not spin? Is it spin like a top or not like a top? And we'll never know. We'll never know. In fact, they can't really, tell you, okay? So yeah, they talk about whether it's right-handed or left-handed, something to do with a spin, but they never define spin. So we have no idea today what they mean by all this. Not a single student of quantum mechanics understands that. Not one can explain that to you. Okay, there's no way because they never defined it. That's why they can't. And what is this chirality thing? Well, just so you see here, it's just handedness, okay? Particles that are not superimposable with their mirror images. In other words, they're looking like that, and you can't superimpose them because they're mirror images. Nothing special there, but again, qualitative. And at the end of the story, you say, well, we don't understand any of this. And here you have one professor from a university, and he's going to tell it to you in his own words, okay? Sometimes it's a little loud, so try to cover your ears. Okay, here it is.
It is impossible to even comprehend. Don't even ask me why. Don't ask me how it works, because it's an illegal question.
So, quantum, no one can understand it. And just in case you have some other professors or celebrities, you could say, of quantum mechanics, and they'll tell you in their own words, so listen to each one of them.
Quantum physics is notoriously weird, strange, and counterintuitive.
To this day, still have great difficulty in understanding it. After you learn quantum mechanics, you're never really the same again.
The short answer is we don't know. This is the fundamental mystery of quantum mechanics.
The most magical thing is that in quantum physics, an object can be in more than one place at the same time.
Because it may suggest that information has traveled instantaneously, faster than the speed of light, from one particle to another. I don't understand it. I don't know that anyone does. Spooky action at a distance, as Einstein called it.
In fact, quantum physics may suggest that reality is simply a figment of our imagination.
So what have we learned after 100 years of quantum mechanics? Well, not much. They say they don't understand what they're talking about. They say that reality may not exist. What do they mean by that? Okay, but the one who says it best is, here we have good old Sabine Hossenfelder. She's a celebrity of mathematics, okay? She's part of the crowd, but she acts as if she were a dissident, of the mainstream. And she said it best. Here it is. Okay, she says, I don't think that anyone knows what they're doing. Yeah, absolutely. I think after 100 years, no one knows in quantum mechanics what they're doing anymore. So they worked 100 years doing equations, doing all kinds of experiments, and no one knows what they're doing. They cannot explain a single phenomenon of nature.